So let's talk about the tank mixing problem. Again, mixing problem. So we have a tank. This tank is holding 1000 liter of water. 1000. So that means it has 1000 liter of water. And then some brine solution is being pumped into the tank at the rate of 10 liter per minute. 10 liter per minute. And the concentration of that, so the brine solution which is being input into the tank is 0.25 kilogram per liter. Okay. And at the same time, some solution is going out, okay, at the rate of 10 liter per minute. So at any time t, the salt solution present in this tank is A, so which is a function of t. So what is the change in the amount of salt in the tank with respect to time? It is equal to the inlet rate minus outlet rate. Okay, right. So the inlet rate is 10 liter of brine times 0.25 kilograms, so which means 0.25 kilogram per liter into 10 liter per minute. So which means it is, liter cancels with liter, so it will be 2.5 kilogram per minute. Okay, so that's the units of the concentration of salt into the water, and minus the outlet. So what is the outlet? Outlet concentration is A. You see, A at any time. A is kilogram per minute, and the rate is also 10 liter per minute. So kilogram per liter. Okay, the rate will be A kilogram per liter, but it's not A kilogram per liter. It is the A is in kilogram. Okay, so this total A is included in to the whole tank. So in terms of the kilograms per liter, it should be A divided by the whole volume, that is 1000 liter. Okay, so now liter cancels with liter, so it will be now A divided by 1000 times 100, so it will be 0.01 A. Okay, 0.01 A. So the differential equation is now dA over dt is equal to 2.5 minus 0.01 A. So we can write it like this: dA dA into times d. So it will be a separable equation. Okay, so I can take 0.01 here, A, and then I can write it like 2.5 dt. Okay, or I can write it in a linear ordinary differential equation form as well. So for example, dA over dt. So it is a linear ordinary differential equation. So its integrating factor is mu is e power 0.01, right, dA. So it will be e power 0.01 a. No, it's not a, it should be t. Should be t. This is the integrating factor. So e 0.01 t times a prime is equal to 2.5 e power 0.01 t. So if we integrate it, so it will be a times 0 e power 0.01 t is equal to 2.5 e power 0.01 t divided by 0.01. Okay, so this will be the, I think maybe I'm making a mistake. So it will be a times 0.01 t into 2.1 and then plus constant. So from here a will be equal to, so I will divide it by e power 0.01, so it will be 2.5 divided by 0.01, it will be 250 plus c times e power minus 0.01 t. Okay, so this is the equation for a, which is the amount of salt. So initially we can assume that at time is equal to 0, this amount of salt was 25 kilogram. Okay, this we can assume. Okay, or it may be given to you. So 25, 250 plus c e power minus 0.01 times 0. So this will be e power 0, that is 1. So from here the value of c will be minus 225. Okay, so what we can find is, if we want to find the amount of salt in the tank, okay, amount of salt in the tank, if we want to find in the long run, that means when times approaches infinity. So in this case, well, if we input the value of c over here, a is equal to 225 minus 225, 250 minus 225 e power minus 0.01 t. So in this, when we say that when t approaches the infinity over here, so we can write like this: a is equal to 250 minus 225 power e power 0.01 t. So when t approaches 0, so this is a very large term. This is a very large term. So this means that this divided by very large term, so then this will approach 0. Then that means a will be equal to 250 kilogram. So in the long run there will be 250 kilogram of salt in the tank. So as another option, if we assume that in this tank the outlet rate is not equal to the inlet rate. So in this case, if you remember now that the inlet rate was same as the outlet rate, but if now the outlet rate is not the same, maybe less, so then how will the equation, the differential equation and its solution change? So when the both rates were same, this was the differential equation. When the rate will be different, then what will be their differential equation? So we know that the dA over dt is equal to R in minus R out. Okay, so R in the same, but what will be the R out? So how can we find R out? So for R out, we will assume that there is salt amount A, and what divided by the total volume of the brine in that case. In this case, now we have assumed that the R out is not same as the R in, so we can assume that the outlet rate is less. Outlet rate is less. So for example, previously it was 10 liter per minute, but now it is 9 liter per minute. Okay, so what's happening is that inlet is the same. So this is the outlet. So in each minute there is an increase of 1 liter into the tank. So each minute 1 liter increase of brine in the tank. So this means that in T minutes, so there will be a T liter increase. Okay, so suppose the amount of salt after time T is A. So originally there was 1000 liter. So then T liter have were added. Okay, so this will be the concentration of salt into the tank. So that means A is in kilogram and this is in liter. And now how many kilograms per minute are going out? So that will be that we can multiply it by the outflow rate, which is 9 liter per minute. So in this case it will be 9A divided by 1000. So the differential equation will be dA over dt equal to R in will be the same, 2.5 minus 9A over 1000 plus T. Okay, so this differential equation can also be solved. It is a linear first order differential equation. You can write it in a standard form like this. Is equal to 2.5, and the integrating factor we can find as follows: E mu is equal to e power integral of 9 over 1000 plus t dt. So this will be equal to e power log 1000 plus t power 9, or it will be equal to 1000 plus t power 9. So we can write this like this: 1000 plus t power 9 times a prime is equal to 2.5 into 1000 plus plus t power 9. Okay, so now integrate this equation. So it will be 1000 plus t power 9 a is equal to 2.5 into 1000 plus t power 10 over n plus c. So in this way, if you will simplify this in terms of a, then the equation will become a is equal to, so after simplification this equation. So a quick examination will show that at infinite time the amount of salt will be also very large, infinity.